You are spending 40 hours memorizing how to write a merge sort in Python, but the hardware running your AI model does not care about your sorting logic. It cares if you know why that sort fails when it hits a GPU memory bandwidth. The popular GitHub repository known as the Algorithms Python has over 223,000 stars, yet for an engineer building modern systems, relying on this resource creates a dangerous false sense of competence. This video argues that memorizing classical implementations is obsolete when hardware constraints and distributed systems dominate production reality. We are shifting from algorithmic complexity to the management of physical limits where your career judgment truly matters. The trap begins with how we measure engineering readiness today. For years, the standard for a good candidate was simple. Can you implement Dijkstra's algorithm in 20 minutes without looking at documentation? That mindset treats code as an isolated puzzle rather than a component within a massive machine. In that old world of interview prep, success meant rote memorization of sorting and searching techniques found on platforms like the algorithms. Python. But this approach ignores the fundamental shift in how we build software for artificial intelligence. The question is no longer about writing code from scratch. It is about understanding why a specific implementation crashes when your dataset exceeds video random access memory, or how to offload graph traversal across a TPU cluster without losing precision. When you look at the data behind these resources, the divergence becomes stark. There are over 17,575 public repositories tagged with algorithms on GitHub alone. Of those, roughly 3,900 are Python implementations, contributing to hundreds of thousands of combined stars. These numbers represent a massive library of knowledge optimized for interviews and academic exercises rather than production scaling. Senior engineers do not ignore the concepts behind these algorithms. They bypass the static code snippets because those isolated functions offer zero insight into distributed systems or hardware bottlenecks. The most starred repositories, often curated by individuals preparing for job markets, function as study plans. They teach you how to write a loop, but fail to teach you why that loop might stall when data movement costs more than computation itself on modern silicon. Quick resource note. I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The real danger lies in the gap between theoretical complexity and physical reality. In AI machine learning pipelines, classical algorithm performance is dictated by constraints that Python wrappers simply cannot solve. Consider memory bandwidth. A sorting algorithm optimized for CPU cache may fail catastrophically if you try to run it directly on a GPU, where data movement costs significantly more than calculation time. If your system assumes the standard library will handle everything automatically, you are ignoring the physical limits of the chip running your model. This is similar to financial models that ignore gap risk during margin periods. They assume stability until volatility hits and the entire structure collapses. In engineering terms, this means a script works perfectly on a laptop but fails completely in production because it does not account for hardware variance or network latency between nodes. This leads us to why modern seniority is defined differently than before. The ability to choose the right library over writing custom code is what separates a coder from an AI engineer. In practice, engineers rely on optimized libraries like SciPy, Sparse, or Torch. Distributed. These tools abstract the algorithm entirely so you can focus on system design trade-offs rather than bitwise operations. When your graph traversal needs to scale across multiple nodes, the algorithm becomes secondary to the data partitioning strategy. You are no longer writing a function. You are designing a distributed pattern where the logic of MapReduce or Spark dictates success more than the specific sorting routine you chose. The most critical skill is knowing when not to write code at all, and instead leveraging existing infrastructure that has already solved these hardware constraints for billions of users. The shift in what we value as senior engineers reflects this new reality. Analysis of top curated repositories tagged with senior developer topics reveals a stark divergence. Only 6% focus on pure algorithm implementation. Instead, successful engineering resources blend algorithms with modern domains like cloud architecture and system design patterns. This is not about telling you to stop learning the fundamentals. It is about revealing that for AI practitioners, Implementation mastery of basic sorting or searching has become obsolete currency. The new currency is architectural judgment regarding how those algorithms interact with hardware hierarchies and distributed infrastructure. If your study plan focuses on memorizing code snippets from a repository with hundreds of thousands of stars without understanding the underlying physics of memory bandwidth and data sharding, you are preparing for an exam that no longer exists in the industry. So what should you do instead? You must stop wasting time memorizing sorting implementations because you will likely never write a merge sort from scratch in production. Your job is to know when not to use it. Instead of studying the algorithms repository for syntax, focus on resources that cover how data movement impacts algorithmic complexity across different hardware types. Study distributed computing patterns where the logic is defined by system design rather than function definitions. Prioritize understanding hardware-aware optimization strategies over theoretical big O notation in isolation. This approach transforms you from an interview candidate who memorized code into an engineer who understands why a system works or fails at scale. The payoff for this shift is immediate career relevance. When you can explain why your graph traversal crashes under load and how to fix it using distributed patterns, you demonstrate the judgment that defines senior roles in AI engineering. You are no longer just writing code. You are managing physical constraints on silicon chips designed for massive parallelism. This perspective allows you to navigate production realities with confidence rather than relying on outdated study guides that treat software as a pure logic exercise separate from the hardware it runs on. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.